All right, recording is rolling. Welcome to a new week, Monday, September 11th. So a lot of fun stuff going on today. Let's start with talking about a linear motion quiz. So here's top scientists for linear motion quiz. Got a couple of AP classes, so if your name's on that list, then awesome. Right, so I know that was the very first quiz in here. This is a really tough class. Some of you guys did awesome on the quiz, some not so much. Right? So here's what we're gonna do about this, like in case you got like a 40 or something. Okay? There's going to be a corrections opportunity. The way the corrections opportunity is going to work is first I have to get all the quizzes in. There were a few students absent. I'm still waiting on like 2 or 3 quizzes. Right. Once I get them all in, get them graded, I'll get those back to you guys. And then I will post the solutions to Google Classroom. Right. You definitely have to post the solutions because I am throwing you guys really challenging questions, like intentionally, because if you guys solve these, then you're definitely going to be good on the exam, right? So these are pretty tough questions I'm giving you guys, like solve in terms of variables, right? It's like a practice that we've been doing in class, right? Everything on the quiz is like some version of something you guys have seen in class, but I have to stretch your imagination a little bit, right? But I'll post the solutions. Then every single problem that you personally missed, if you missed some, right? Definitely got some hundreds on here. Some of you guys got hundreds, right? But if you missed any, then what you can do is handwrite out the solutions, show how you get to the solution, based on, well, I'm going to post the solutions, right? If it's a graph, you can just draw the graph, and I will give you guys partial credit back. Okay? So that's how we're going to do that. Okay? Haven't handed those back yet, but in time. Okay? So you guys get on that linear motion and corrections opportunity. All right, projectile motion. You guys know we're wrapping that up. You guys just turned in your chapter 3 puzzles. Thank you for doing that. I want to take today just to do like one final review day, just do some more projectile practice with you guys, and then tomorrow we'll get started on the next section. Okay? So I do have a take-home quiz for you guys. I want to go ahead and do the review first, and then hand you guys this. So this will be another take-home quiz. This will be due in a few days. So you have a few days, sit down, think deeply about these problems, and try stuff out. Okay? Just like with the linear motion, there's different versions of them, but they're all about equally difficult. Okay? Right, so I have gone ahead and opened up the next section on AP Classroom, Unit 2. Unit 2 is like forces, dynamics, Newton's laws of motion, that sort of thing. Right, that's what we're going into. This one's not due for a few weeks. It's going to be on a Monday. Right, now, have this done by the time you guys come to class on that Monday. Right, which again is a few weeks from now. You guys are writing this all down in your plan, right? All your plan. Okay. Right, so that my plan is to go over the solutions that particular Monday. I think by then, you guys will get the hang of this topic enough. You'll be able to answer those questions, right? I think it's like 20-something questions there, right? Multiple choice. Right. Also, I gave to you guys when you guys were walking in. Oops. A couple of pages. Oops, I'm sorry, that's here we go. Okay. So you guys have chapter 4 questions from your book. The ones I'm going to pick up, now this will be a few weeks from now, like the end of the month, on the 29th, I'll pick these up for you guys. Okay? I'm looking for, well, it's the same ones I circled. I just went ahead and wrote out the list right here, ones I circled. But if you're at home and you're printing these out, then right, okay, you see these right here. Right? So there's a warm-up section, which I circled 5 of those. Right? There's a bunch of other ones here. And then there's the main problem section, and I circled a bunch of those. Right? I'll do as many as I can in class with you guys, like walk over. But you guys know we got lots of other things to do in here. I got like many labs lined up for this section. We've got other AP stuff. I want get some FRQs to you guys, that sort of thing. Right? Just like with linear motion, and projectiles, the solutions to these have already been posted, right? And you guys know how those work, right? So make sure you can actually do these with like piece of paper by yourself. Yes.
Those questions are these, right?
Yeah, this one says chapter 4.
Okay.
Right? So the first section is warm up, and it's the same ones as are circled. So just whichever ones are circled. That's what I'm looking for. If you can do those, then you're pretty good. If you need some more practice, well, there's lots more on here, also with the solutions. Okay. I also gave you guys this staple packet. So the first page is 20 questions of conceptual questions on Newton's first law of motion or related to. Then second page, Newton's second law of motion, 20 conceptual questions. Third page, Newton's third law of motion, 20 conceptual questions. I don't know if I'll have time to do like all the Kahoots on those. I might do a shortened version of a Kahoot, maybe. We'll see next few weeks. Okay. On the back, you guys see some of the posters printed. Had an extra page, kind of put something on it. Like, ooh, right. You guys do see there's new posters cycle through. You guys see new posters cycle through? Right. So you guys got new stuff here. There's like 20-something posters for the section I have. I went ahead and picked what I thought would be like the top 6 because that's what I could fit on the page. So here you go. Here's our there's some notes. You guys got a head start on the notes, right? You guys good? All right. Here's a brief overview. All right, so let's take the rest of class to do a review of projectiles, and then hopefully I'll have about 4 or 5 minutes at the end of class. I can help you guys set up this spring lab tomorrow. Okay. All right, here we go. So here's a question that's been stuck with students all day. Well, actually, there's a couple of questions. The first one's not too bad, but the second one's it's a real stumper. Okay. Zookeeper devises a rubber band gun, so a slingshot, to shoot a banana to a monkey who is too shy to come down from the trees. Oh, look, we got slingshot, banana. Here's the monkey. If the monkey does not move, right, so the monkey's just gonna hang onto that branch, should the keeper aim above, at, or below the monkey? Show hands for above. Who says above? All right, you guys are right. Unless, hey, well, what if you just, you guys know we play around with variables in this class, right? What if you turned off gravity? There's no gravity. Now what's the answer to that question? Right at it. Will that banana just follow a straight line path? Okay. Actually, that's Newton's first law of motion right there. Newton's first law of motion. If there's no external force, it just wants to follow a straight path. Okay. Turn gravity back on. Okay. Now, how hard does he have to fire at the monkey? Well, it depends on a lot, or I should say what angle above is what I meant to ask. What angle above that dashed line? Okay? Depends on a lot of things. Depends how fast he's firing it. Depends how far across it is to the monkey. Depends how high the monkey is. And also the strength of the gravity field for that matter, if you want that to be a variable too. Okay? He aims it kind of fast, shoots it kind of fast, maybe like barely above. Okay? If he kind of lobs it, or monkey's far away wave, it's but so some version of a parabola. It's gonna get to that monkey. Okay, so that's not fun good. Now here's the stumper question. I wonder how many students are gonna get this right. If the monkey lets go of the branch at the instant the keeper fires the banana, right? So they both release at the same time. In that case, should the keeper have aimed above, at, or below the monkey? Right? Oh, also here's another stipulation. The monkey's going to catch the banana before he hits the ground. Okay, so the monkey is going to catch the banana mid-flight. Right? Maybe up here, maybe here, maybe here, but before he reaches the ground. Okay, you guys go with that. Now let's see. Show of hands. How many of you guys think he should still aim above the monkey? Still aim above the monkey. All right, all right. Who says at the monkey? Got it. Okay. I think we got 1 or 2 votes here, about 5 votes here. Who says below the monkey? Right. Ooh, about 5 or 6 votes there. Okay, all right. So if you said at the monkey, ooh, that's what we're looking for. We're looking for right at the monkey. Okay. Now, why would that be? Why is it if you aim right at the monkey, release, okay, you fall at the same time? Yeah.
Both the projectile and the monkey are being affected by gravity at the same rate, so I guess it doesn't matter if you shoot above it or no, that's not true. They're both being affected by gravity at the same rate, so they both be falling at
right.
the same rate.
Yeah. There you go. Gravity's gonna pull on them the same. Okay. Now for the monkey, it's real straightforward. That's just linear motion. How far it falls, let's say it's a function of time. Let's say it's fall a quarter second, half second, 1 second, whatever. Right? However far it falls is like h equals 1/2 gt squared. You can use a simplified version of this one, right? Starts from rest, this goes away. Oh, there's the college equation. How far he falls is 1/2 gt squared. You guys see that? Okay. Now the banana, see, like if there was no gravity, the banana would follow the straight line dash path. Okay? But if you turn gravity on, it's going to deviate from that path. But how much does it deviate from that path? The exact same amount, 1/2 gt squared. Okay? This x could be a general displacement variable here. But what if I turn this into y to represent like a vertical displacement? We can make this y or h, right? This y or h for here, right? This could be v naught in the y direction. See, like how fast is it moving upwards, okay? This could be, okay, and then, okay, I do like a minus here, minus 1/2 gt squared. So I could, if he's firing up, the gravity's pulling down. Yeah, and the amount that the banana deviates from this dashed line, right, as a function of time, is going to be the exact same amount that the monkey falls for the same amount of time. Yeah, right. So that's a pretty tricky one there. Okay. Right, how about, we're going to do 2 more from this book. Speed of an airplane relative to the ground is affected by wind. When the airplane flies in the direction of the wind, tailwind, it gets a greater ground speed, gets a boost. Wind's pushing it. If the airplane's flying directly into the wind, headwind, it's a smaller ground speed. They're fighting each other. It's a fight. Okay. But what about what's going to happen to its ground speed? So there's some guy on the ground that points a radar gun up at it. when there's a 90-degree crosswind. Suppose the airplane flies with a 90-degree crosswind. Will its ground speed be more or less or the same as compared to the air? Show of hands. How many guys say more? Who says a greater ground speed with a 90-degree crosswind? Okay. Who says less? And who says the same? Okay, it looks like most of you guys remember that it's going to be more. But this one I want to go ahead and draw out. So you guys did see this one last week. I think this was on a Kahoot. This is where it was. Okay. So let me show this mathematically with vectors. So suppose the plane is pointed straight north and it's flying at 40 meters per second. Now the propellers can only push against the surrounding air. So all the plane like really knows about it, anthropomorphize the plane, is like pushing against the air around it. Okay? But what if that entire air mass was moving to the east at the same time? Let's say like 30 meters per second. Ooh, that would be wind. Okay? Okay. So here's the plane relative to the surrounding air. Here's the air relative to the surrounding ground. Okay? Now the plane's always pointed north. It's not necessarily moving straight north, but it is pointed north. Okay? The air everywhere is moving to the east. Notice I connected those tip to tail. You guys see tip to tail? That's what you do with vectors, right? To add vectors. Okay? I only have 2 vectors here. If I had 10 vectors, I could just keep linking them like that. Okay? If you go from the tail of the first one to the tip of the last one, what's this vector called? What's the name of it? It starts with an R. The what vector? Resultant. Oh yeah, there's the resultant vector right there. Okay? And that tells you both the direction the plane actually moves. It's pointed north. It actually moves kind of northeastish. Okay? And also the magnitude of its velocity relative to the ground. So like its speed relative to the ground. Right? Take a look at that and tell me how fast is that plane going on the radar gun?
50 meters per second.
50 meters per second. Right? Okay. And in general, you could do Pythagorean theorem. Right? 40 squared plus 30 squared. In this case, then meters per second. Yeah, and I did set up a what triangle? 3, 4, 5 proportional triangle. Okay, so nice numbers on that one. Ooh, direction. What angle is that right there? How do you get it? How do you get it? Inverse tan, whatever what. There you go. 30 over 40, opposite over adjacent. Right? By the way, that comes out to almost 37 degrees. I'm going to say east of north. East of north, right? Right? Now we have a magnitude and a direction. Boom, boom. 2 aspects of a vector. Right? There we go. All right, let's do one more of these. Boy on a tower throws a ball. Right? It looks like he throws it straight horizontal, and it arcs into a parabola shape. Right? And it lands 20 meters from the base of that tower. Right? What's his pitching speed? Who sees his pitching speed? Who sees his pitching speed? How fast do you throw that ball? It's about a 5-meter tall tower. 5-meter tall tower. Went 20 meters across. 20 meters a second? Right, 20 meters a second? Because how much time would it take to reach the ground? 1 second, right? Right? You guys remember that? To fall 5 meters takes 1 second. Or if you drop a rock in 1 second, it falls 5 meters. Right? Actually, these are rounded a little bit. We've been using 10 meters per second squared for gravity. Looks like here they probably went with 9.8 meters per second squared. Right? Okay, so it's a slightly altered version of the height of that tower. This was your guys' lab. The last lab you guys did was this question right here. Right? You fired a projectile. You measured the height of the balcony. You guys measured, you spotted where the ball landed and took out the trundle wheels. And you back calculated how fast was it thrown. Right? So there's 2 parts to this. Right? You're juggling vertical and horizontal. Vertically, you could say h equals 1/2 gt squared, right? And you get, okay, took a second to fall. Right? H equals 1/2 gt squared. Once you got that second, okay, took a second from here to here. Okay, well, it must have been going across 20 meters in that second. Okay, he threw it 20 meters per second. You see that? Right, so you're juggling 2 different variables, 2 different dimensions. Okay, you guys good? All right, let's put those aside. All right, and I want to walk you guys through a couple of projectile examples. Hopefully pull up the strength scale class 4 or 5 minutes of class. See how that works out. Go through a couple of projectiles. So let's start with the classic setup of pretty much what we were just looking at. Let's do cannon at the edge of a cliff type deal. Okay. So cannon, edge of a cliff. Let's just blast it straight horizontal. Now I could call it V blast. I could also call it V sub X because the cannon is already oriented horizontally. So whatever speed it's blasting is just going to stay like that, right? And this, bam, something like that, right? Okay. Ooh, nice parabola there. Here's the vertex of the parabola right in front of the cannon. Okay. All right. This cliff could be some height, and this ball could land some X out there. Okay. Here's some gravity field that's causing it to curve down like that to a parabola shape gravity field. And if you knew any number of these, you could solve for everything else. Like if I told you these three variables on here, you could probably calculate what planet you're on, like what the gravity field was. If you assume that you're on Earth, I could give you two of those three things. You can solve for the third one. Okay. Let's make up some numbers here. Suppose this cannon is blasting. I'm going to come up with some numbers that I'm pretty sure are not on any quizzes. Let's go 1,000 meters per second. Okay. Let's say the height of this is like 45 meters. And I'm trying to figure out how far does that cannonball go. Some of you guys might be able to figure that out without writing anything down. Maybe. Give you guys an opportunity first before I start plugging and chugging. Who can figure out how far from the base of the cliff that cannonball lands? What you got, Steve? Ooh. Okay, I think you're a great idea. 1,000 meters per second. Ah, right. There you go, 3,000 meters, 3,000 meters. How do you know it's 3,000 meters?
Well, it's 45 meters high.
Boom, right? H equals 1/2 GT squared gets you, okay, so 3 seconds it would have been falling. Okay. There you go, right? Oh, yeah. now this poster's hanging in the back of the room. Somewhere back there. There it is, I see it back there. Okay. And then, if you know it's been in the air for 3 seconds, it's been going across at 1,000 meters per second, must have landed 3,000 meters away. Boom, boom, like that. Okay. Let me go ahead and write that down. So I'm going to start with the vertical info. Okay. That's going to constrain how much time it was in the air for. Okay. I'm going to say H equals 1/2 GT squared. I'm going to start like that, right? Okay. Oh, hang on a minute. Actually, can I say that? Because you guys know I'm using a shortened version of this one, right? So I'm thinking vertical. That's why the general displacement, I went ahead and called it H, like a height of the cliff. That's okay, right? 1/2 GT squared could be this bit. Right? But hang on a minute. Isn't that cannonball being blasted really fast? Can I really say initial velocity 0? It looks like that's what I did here. Is that okay? Why'd I call it 0? Yeah, why? Bam, exactly. Guys, this is a horizontal velocity. This equation is set up vertical. When that cannonball is leaving that cannon, it's not moving up or down at all. Okay, this is initial velocity in the y direction. Maybe I should add to the subscript, v not y, right? We can always modify this, right? Okay, so in this case, right. So we're just gonna use the college equation here. By the way, if you just let a cannonball just like barely roll off the edge, that's to have the exact same vertical motion. It sure would. They hit the ground at the same time. It's that right there. Okay. Solve for t. Since you guys are AP, be really comfortable with solving in terms of variables. Times 2 divided by g, 2h on g is your t squared. Therefore, square root both sides. You guys remember that right there? Just remember that? Right. You guys seen this at least a couple of times. When you were solving the backwards version of this for your lab, like when you spotted where it landed, you were trying to figure out how fast. Right. This was also a middle step along the way, like time of fall. Right. Also, you guys remember doing the ruler? Like you held a ruler, dropped it, your partner caught it as fast as possible. Reaction time. That was that right there. There's your reaction time for dropping a ruler. Same thing. Okay. So let's pop in some numbers here. Maybe a pinky ball. Plug in the numbers. 2 times 45 meters at 10 meters per second squared. Guess what's 2 times 45? Divided by 10? Square root? 3 seconds. 3 seconds about. Right? Maybe if this was an AP exam, I'd say 3.0. Just keep a couple of digits. You guys get the idea, right? 3 seconds? Okay. All right. Now let's switch over horizontal. Horizontal. Okay. So horizontally for projectiles, there's only one expression that I ever can really use. What equals what times what? Yeah, dx times c. That's it, right? there's no acceleration. There's no like, if you want to go equation shopping, like, which one of these would it be? Well, if acceleration is 0, then the bottom two aren't really that exciting. Right? The top one just boils down to x equals vt. Right? That's all we got. Right? Yeah, horizontally. Gravity doesn't pull horizontally. We've been ignoring air drag. So there. Let's just take this time, pop it right in there. Or maybe this expression if you want to do it in terms of variables, right? So some version of that. Okay, I'll break out some numbers. X we're solving for equals 1,000 meters per second. We'll do that for 3 seconds. Okay. Looks like 3,000 meters. Voila. Okay. Or if you like, in terms of variables, it looks like it's going to be the blast speed times this funny expression for the fall time, right? In terms of variables, right? You guys can solve numbers. You guys can solve in terms of variables. Okay, you guys good there? Okay. Ooh, you know what else I'm wondering though? Now that I'm looking at this, I wonder when this cannonball crashes into the ground right here, right? What is the velocity of the crash? What's the crash velocity? And velocity has 2 aspects: speed, but also direction. Okay? Wonder what speed and direction it's coming in right there. Okay? So since this side of the paper is getting pretty crowded, I'm just going to take this and start over and blow it up right here. Let's go. Ground. Okay. Here's like a shallow parabola, so it's coming in. Right, and right there, bam. Right at that instant, it's kind of coming on that angle, right? Right. So the cannonball actually follows this parabola path, but right at the moment of collision, it's traveling like in this direction. Okay. I'll call that V crash. Okay. Now to make sense of that, to figure out the speed and direction, what's going to lead into that? I have to break this into what starts with the C. Components. That's what I'm looking for. Components. Right. So here's how we're going to piece this together. We know it's coming across. We know the cannonball is coming across the field. We also know it's falling down at the same time, coming across and falling down. Okay. Now the v sub x. Okay. We know what that is. That was given as 1,000 meters per second. That doesn't change all the way across the field. Right? Now the y direction is a little trickier. I can't just call this v sub y. I call it v initial on the y direction, or sometimes you see vy initial. Those subscripts might be opposite direction. That's sorry, not initial. What am I doing? Final. Oops. The initial in the y direction would have just been 0, but the final in the y direction, right? Okay. Now there's a couple ways you can get this. Does anybody know what the number is going to be for what we've been doing so far? How fast is it coming straight down? How fast is that cannonball coming straight down? 30 meters per second. Boom, you got it. 30 meters per second. Okay. How do you know it was 30 meters per second? Boom, that's it. Right? Gravity times time. Right? If it's been falling for 3 seconds at 10 meters per second squared, it's been picking up. Yeah, picks up to 30 meters per second. Right? Alternatively, you could have played off the height of the cliff. You could say, well, anything that falls 45 meters also would have picked up to 30 meters per second that way, playing off this third kinematic expression. Right? So you guys did g times t, got it that way, perfectly valid. You could have played off the height of the cliff and gotten the same answer. Yeah, you're right. Okay. So let's do this. Here, I'll do it the way you guys said. You guys said, let's do 10 meters per second squared times 3 seconds. I guess in general, that would be like g times t. Okay. All right, so 30 meters per second. It's fun. Okay. Okay. So how would you find v crash, the magnitude? Yep, square root of that squared plus that squared. Put that all on my root bar. Right, meters per second. Okay. By the way, I picked a ridiculously fast blast speed just so it would show up on anybody's particular quiz. Right. This ends up being like a shade over 1,000 meters per second. It's like 1,000.4 or something ridiculous meters per second. Okay. I should say too, this blast speed that I'm picking, we point out something about this, is orbital speed around Earth is like 8,000 meters per second. So this is kind of the maximum I can go before you have to start considering, well, the Earth actually is curved. It's not exactly flat. And now we're like almost like coming up against like a suborbital type of velocity here. That's probably as fast as I can get the cannon going before we run into that, right? But yeah, so we got something like that, right? Oh, the other question then would be, what is this angle? Like, what's the direction of crash? Okay, and how would you find that? Inverse tan of whatever what? Yep, opposite over adjacent. Meters per second, whatever. Okay. By the way, this comes out to about 88 degrees from the vertical, okay, which is a really extreme case. I mean, that's almost a 90-degree angle, right, from the vertical. Right? That means that's a really shallow parabola. Right? That cannonball went a long way, like 3 kilometers, just to fall like 45 meters, right? So it's a really shallow parabola. That cannonball's just going to point, like skip like that. I think. Let's get that. Right? You guys good? Okay. So there we go. All right, any questions on that one? All right, let's do the other classic setup we can do with projectile motion, which is we're going to put a cannon on a plane. We're going to blast this thing at some angle. So there's your plane. There's the cannon. Okay. It's a cannon barrel. We're going to blast this thing up. Let's have the same cannon that we just had. Same cannon. Okay. So I'm going to call this V blast equals 1,000 meters per second. Right, just a ridiculous cannon. Oh, and you give you guys an angle. Let's go with theta from the horizontal equals 53 degrees. How about that? 53 degrees. Okay. Okay. Now, there's 2 questions I want to tackle with this. I want to know like how far does it go? Oops, forgot to draw the path. So do a nice parabola right here. Okay. I would like to know how far it goes. Maybe I'll call that x. Right? What's this horizontal displacement? Right. I might also want to know like what is this maximum height? That'd be kind of nice to know too, right? But I can't make sense of any of this until I do what to this first? Break the components. Yeah, break it into components. Right. Right. So I need to analyze this in terms of like, well, how fast exactly is it traveling across the field? And how fast was it initially traveling straight upward? Notice I dashed those components. See, I dashed them. See, if I do them solid, if you do it like that, if you make them solid, your component solid on an FRQ, the AP score will give you no points. Okay? So if you draw them at all, make sure that you dash them. Okay? So this leg right here, I'll call it V sub x. Okay? Now, in general terms, this could be V blast times what? Sine or cosine of this angle. Yeah, cosine of that angle from the horizontal, just like that, right? If you plug in some numbers, let's go 1,000 meters per second times cosine at 53 degrees. Okay, that'll be about I think I'm just gonna call it an even 600 meters per second. Okay, so we're going 600 meters per second. All right. Okay. Now, what about this vertical component right here? Now, this one, I'm not going to exactly call it V sub y. I'm going to call it V initial in the y direction, right? Because gravity is immediately going to start changing that. Like 1 second later, it's going to be going slower. Okay? Horizontal is a lot more straightforward. V sub x is just V sub x. That's the same way all the way across. That V sub y, it's going to shrink on the way up and it's going to grow on the way down because of gravity field. This is, in general terms, V blast times what? Sine of that angle from the horizontal. Plug in some numbers. Let's go 1,000 meters per second times sine of 53 degrees. You should get about 800 meters per second, probably even 800 meters per second. Right? Okay. Okay. You guys set? Okay. I like setting up 3, 4, 5 triangles because hopefully a little bit easier to digest. Like you can see the big picture of what's going on. Okay. All right. Okay. So if you want to figure out like how far does it go, that's our first question. How far does it go? Okay. I definitely know it's headed across like 600 meters per second from up here in a blimp. Watch this whole thing. Looks like it's going pretty well across the field, 600 meters per second. If only I knew how much time it was in the air for. But what's going to constrain the amount of time? Horizontal or vertical information? Vertical. Definitely vertical, right? How fast was it initially going up? And how much is gravity pulling down? Those are the 2 things that are fighting each other. Right? So I'm going to switch over to vertical, do some vertical analysis so that I can get the hang time. Now, there are several different ways you can get the hang time. I'm going to walk you guys through two for this review, through two different ways. Okay. One way is you could break this problem in half. You can say, well, how much time does it take to get to the maximum point? The reason I'm taking it this way is because we're going to do something about that later so we can calculate maximum height also. Okay. We break this problem in half. It's going to take some amount of time to get up here. And it'll take the same amount of time to fall back down because it's symmetrical. So whatever this time is up to here, we just like double that. Right? Now, if you do it that way, think about this. I know how fast it's going upwards, 800 meters per second at the point of the cannon, 800 meters per second straight up. Okay? At the very top, what is its vertical component of velocity right at the very top? 0 meters per second, right? Now, the cannonball is still moving to the side really fast, but vertically speaking, it goes to 0, right? It's not quite going up, it's not quite going down. Okay? I'm going to break out this guy right here. V final in the y direction equals V initial in the y direction minus G times T. Okay? But I want to make sure I know what time I'm talking about. Guys, is this the full hang time? Or is this what fraction of the hang time? Half the hang time. I'm going to throw a subscript that says half, so I know that's half of the hang time. Okay, that's kind of what we're solving for. Right, you guys got that? Okay. Now, you should be pretty comfortable with solving in terms of variables. Some of you guys might possibly get a quiz that says solve this in terms of variables. I'm just going to go ahead and plug in some numbers at this point. Okay, if this is half the hang time, we already know that this is set equal to 0 meters per second. Right? Final velocity in the vertical direction. Right? I mean, this and this go hand in hand. Half the hang time, oh, that's 0. Right? This number happens to be 800 meters per second for this particular question. We pull down at 10 meters per second squared. And T half. Okay. Little algebra switcheroo later. Subtract over 800, divide by -10. What's half the hang time going to be? You guys see 80 seconds? You guys see 80 seconds? Okay. And this is a ridiculous cannon. I mean, for it to get like, takes over a minute to get up here. But okay, let's go with that, right? Okay. And if that's true, then what's the full hang time? Yeah, 160 seconds. Takes a solid like 2.5 minutes to shoot. Okay, right? You guys got that? Okay. Now, let me pause here so I can show you at least one other way that you could get hang time. Again, there's several ways to get hang time. Okay? So let's do an alternative, right? It's good to be able to do things multiple ways. Okay? I'm going to use this top expression like for displacement. Now I'm still doing vertical, so general displacement I'm going to replace with like y, right? So vertical. Okay? I'm going to go ahead and get it all in one shot. I'm going to go from here to here. Okay? Guys, what is the vertical displacement from the ground back to the ground? 0, right? Now horizontally it went a long way. We're eventually trying to find out, right? But vertically, there's no change. You see that? Okay. So I'm going to do y equals v naught y t, and this would be the full hang time, minus 1/2 g t squared. Okay. I'll let this guy go to 0 meters. I know this was 800, is that right? Yeah, 800 meters per second times the full hang time. Actually, here, I'm about to do something a little tricky here. Okay. Nah, here, I'll write this way. Okay. Times hang time. Okay. Minus 1/2 times 10 meters per second squared times t squared. Right. Now, at a glance, see, we're solving for t. Does it look like we need to break out the quadratic formula almost? Okay. Almost, except because it's equal to 0. Watch this trick. Okay. I can just factor a t out. 800 meters per second minus 1/2 times 10 squared t. I can factor t out this way. Divide both sides by t. It just goes away. We can skirt right around, never have to pull out a quadratic formula. Right? Is that? Or you could go quadratic. That's okay too, but this is the easier way, right? All right. So divide everything by 10. Subtract this over times -2. The algebra steps later. It's still 160 seconds, and this would be the full hang time, right? Because we're going from the ground back to the ground. Right, so there you go. Got the same hang time we got before. So there's at least 2 different ways to get hang time, right? Guys got? Okay, everybody good? Okay. Again, I solved this with numbers, threw some numbers in here. You guys could solve this in terms of variables, right? Okay. All right, so back over here. I showed you guys 2 different ways to get the amount of time it's going to be in the air for. Okay. Let's switch over to horizontal horizontal. So we can figure out how far does this go? What is this x right here? How far does it go? Okay. And for that, there's only one expression we could possibly use. X equals what? What times what? B sub x times t? Wouldn't that be the case? Right? So let's put some specific numbers in here. X equals, how fast is it going across? 600 meters per second. Yep. Let's book it across at 600 meters per second. Does that for how much time? 160 seconds. Boom, boom. Now, let's see what this comes out to. I'm looking at 96,000. Ooh, guys, that's 96,000. What unit is that? Meters. How many kilometers is that? 96 kilometers. Right. That's an extremely huge number. Right? This might be the biggest projectile example I've ever given. Right? So just for scale, that's approximately halfway from here to Tampa. Right? You guys see this is running up against the idea that like the curvature of the Earth is going to start to matter after this, right? Okay, right. But maybe we're like just in the range. It's like, okay, that's probably still pretty close. Okay. There we go. Okay. Do you guys think you could solve for x just all in terms of variables? I know I have a lot of pink ink with numbers in it. Could you solve it in terms of variables? In fact, I think you guys already know what the answer to that's going to be. What is the answer in terms of variables? It's this guy right here, right? Notice that it cuts through time. If you know the velocity of the cannon, what planet you're on, and the angle you have it pitched at, right? Do you guys remember the other day I showed you, I uploaded a bonus video to Google Classroom. In that bonus video, it's about 14 some minutes long. Okay. I take you guys through the complete derivation of this. So I do what we just did, but just without numbers. It's all in terms of variables. I show you exactly how to derive this. Okay? And furthermore, you could take this expression and you could prove the optimal angle for the furthest horizontal displacement is a 45-degree angle. Right? So I show that too. Right? So yeah, check that out if you haven't yet. It's one of those videos that like, if you need a long explanation, you can just sit there and watch the whole thing. If there's parts of it you understand, you just kind of skip ahead 30 seconds at a time until you run into something like, oh, actually, I need to see this part. Okay. Guys get that? Okay. So the other question I want to tackle here is how high does the cannonball go? We haven't quite answered that yet. How high does it go? Well, guys, if you want to know how high does the ball go, maybe I'm starting to shop these again. Now, again, we're thinking vertical. So we're seeing next, maybe think H or Y or something. Right? We're thinking vertical. Right? Which one of those can you not use to answer how high does the ball go? Which one can you not use? Exactly, the second one. Because this one doesn't say anything about displacement. I mean, there is a displacement, it just doesn't really address it. But these two guys both address displacement, don't they? Right? I bet you could use either one of these and somehow get the maximum height. You guys think? Right? Eeny, meeny, miny, mo. Let's go with this guy right here. How about it? Okay, I'm just gonna pick one. Okay. If you want to check the other way, then feel free. Okay. We're gonna say, how high does this go? So let's say H max equals V naught Y T minus 1/2 GT squared. Okay. This is one way to do it. There might be multiple ways to do this. Okay. So H max equals, I guess I'm doing specific numbers. Okay. It was being blasted up initially at 800 meters per second. What am I going to plug in for the time? 80 seconds. See, if I do the full 160, I'm just going to get 0 and back on the ground. 80 seconds will take me to the maximum height point, won't it? 80 seconds corresponds to here. 80 seconds minus 1/2 10 meters per second squared times 80 seconds squared. Right? Okay, all good. Check this out. What's the maximum height of this thing? 800 by 80 minus 1/2 times 10 times 80 squared. Okay, that's 32,000 meters, or if you like, you call that 32 kilometers. That's higher than Mount Everest. There you go. Okay, guys, go back. So someone pointed out earlier today that, hang on a minute, you could have just treated it as the falling part. You could have said, how far does it fall? It would have been the same height, right? Just the falling part. which more simply just narrows down to 1/2 GT squared. Let's see if that's really true. 1/2 times 10 times 80 squared. Should this be the same thing as 32,000? Oh, it is. It's the same thing. Right, guys good. A little bit different perspectives there. All right, guys good. All right, we got just enough time. Right, we're doing good on time. Here, let me do this. Okay. Let me get you guys your take-home quiz, your next take-home quiz, while you guys are digesting that. Okay, so it looks like this. This will be due on Friday. Take-home quiz right here. Then last few minutes of class, I want to introduce you guys to spring scales and what you're doing in your lab tomorrow. All right, so we're moving on to forces, dynamics. Right? We're going to be talking about like pushing and pulling on things. Right? A force is very simply a push or a pull. I can push on something, I can pull on something. Weight, ooh, that's like a force due to gravity, like pulling straight down. That's a type of force too. And we can quantify forces in the metric system in terms of newtons. Got some spring scales here. Some blue green spring scale, the brown spring scale, and then these big guys over here. Right, that's roughly in order. All right, these scales. Here, let's check this out. On one side, they say how many newtons. Right, so here, if I pull on it, I feel some like resistive force. It takes more force to stretch it further. Right, and how many newtons of like pulling? Right? What's the force? And this is scaled linearly. 0, 2, 4, 6, 8, 10. Okay, that's a linear scale. Huh. Right? See that, right? On the opposite side, it says grams. Okay? The idea is like if you pick something up, right? You guys see, I pick this up. Okay? Now if I stop this and turn it sideways, it says about 5 newtons. About 5 newtons of gravity force this way. If I flip it over to the other side, it says like 500 grams. Now here's the icky thing about this. You guys know grams refers to a mass, right? But this is actually reading what? A mass or a force? That's like a force, like a weight, right? The grams only works at the surface of Earth. It's like, well, what mass would have produced that weight that would read that scaling? So, guys, tomorrow when you're like pulling stuff around and you're reading the scales, do you care about the grams or do you care about the newtons? Newtons, guys, always use newtons for the spring scales, okay? That's all I care about, these newtons, okay? And how much will each scale stretch? Okay. Well, okay. Let's look at some of the notes I printed out for you guys, some of these posters. You guys see this one on the top left says Hooke's law. You guys see Hooke's law right there? Okay. This is the relationship between how much force you put on a spring and how much it stretches or compresses for that matter. Okay. Now, spring scales we're just stretching them, but you might see sometimes we're like compressing a spring. Right? So here's like an unstretched spring right here. Okay. If you put some force on it to pull it, it'll stretch out. How much? Let's suppose it stretches amount X. Okay? And you applied force F to do that. Okay? There's a direct relationship here. You guys see if you like triple the force, it'll also triple the stretch amount. The amount of stretches. You guys see that? Right. Some textbooks throw a negative sign here because they're talking about the restoring force. They're talking about like this gray force right here. Like if you stretch it out, the spring pulls the other way. I usually drop the negative sign, but if you ever see one there, that's what they're talking about. Okay. What else we got? Here's like compressing it. Some idea. You guys are gonna be stretching your springs. Okay. Oh, and look at this. So F equals KX. That's Hooke's law. Right. So got a direct relationship here. Let's look at these different spring scales. Now the brown one is probably the most versatile one. It has like a medium stiffness. Oh, this would say K. This K represents spring constant, which on this graph is like the slope of the graph, right? It represents spring constant. How stiff is that spring? Okay. The blue and the green ones are good for like really light weights, right? So very small forces. Notice it only takes a little bit of force to stretch that a good distance. That's like a little bit of force for a long distance. That's like having a graph that was like really shallow like this for the small K, small spring constant. Okay. Versus like this gold one on the other extreme, it's really hard to stretch that. Put a lot of force and it barely stretches at all. That's like if I had a really large force and it barely stretched it off. Hey, that'd be like having a line that was like this, that was really steep. With a huge slope, that'd be a large spring constant, right? You guys see that too? Right? Okay, now I'm gonna have you guys do different setups for your lab tomorrow. Let me see if I got right here. Okay. I'm gonna give you guys this page tomorrow. It's really gonna be like 10 mini labs is what it's gonna be. I'm gonna have you guys do a bunch of things. Hang stuff. What if you have 2 springs and hang it and like jostle back and forth? Right? Ooh, what if you make this like Y shape and stretch it out more closer to a T? Ooh, it looks kind of like this poster here, maybe some version of that. Right? Ooh, what about this vertical chain gang going on? Ooh, AP likes problems like this. Right? What if you like have some motion, like accelerated it up and down? Ooh, what happens when you like drag it across the table? Get some to do with friction going on. Right. So yeah, tomorrow you guys get to get with your friends. I'll give you guys one of these pages, and you have like these 10 maybe labs. Now pay real close attention to what you're doing tomorrow because I'm going to reference these like many times in the next coming weeks and throughout the year. Right. But there's going to be some AP questions that are like straight off that page right there. All right. Yeah, just in time. All right, any questions today? All right. You guys have a great afternoon. I'll see you tomorrow.